Hey there. Ever looked at a photo and wondered how a computer could know the shape of an object just from light and shadow? It's like magic, but actually it's science. Today we're diving into a breakthrough called LINO-UniPS, a smart AI system rewriting the rules of how machines see the 3D world. Let's break it down. Imagine trying to figure out the shape of a basketball. A single photo under a lamp shows it's round, but switch to sunlight and shadows shift. Now, what if you had dozens of photos under different lights? How would you tell the real shape from the changing light? That's the core challenge of photometric stereo, a field that's way harder than it sounds. Traditional methods require exact knowledge of light positions. But real-world lighting is messy: clouds, reflections, flickering bulbs. It's like solving a puzzle with missing pieces. That's where LINO-UniPS steps in. It's not just a tool. It's a clever AI that learns to ignore lighting chaos and focus on the object itself. So how does it work? Let's dive into the magic. First, the system takes multiple photos of the same object under different lights. These images are like clues. But here's the twist. Instead of assuming light positions, LINO-UniPS learns them. It uses wavelet transforms. Think of them as digital microscopes that zoom into tiny details, like wood grain or vase curves. This helps the AI spot both big shapes and superfine textures. But here's the bigger hurdle: light and surface details get mixed. A bright spot could be a light source or a bump on the object. To fix this, the researchers created light registers, memory slots storing lighting patterns. Then a global attention mechanism lets the AI step back, focusing on the object's true shape instead of flickering lights. Imagine painting a portrait. The sun moves, casting shifting shadows, but you need to capture the subject's face, not the light. LINO-UniPS is like a painter who learns to ignore the changing light and focus on the real details. And here's the kicker: they didn't just improve the algorithm, they built a massive synthetic dataset called PS-verse. Think of it as a virtual training ground, with objects of all shapes and lighting conditions. This lets the AI practice on everything from simple spheres to complex textured surfaces. The result? A system that outperforms existing methods by disentangling lighting from geometry with unprecedented precision. The team tested 10 lighting setups, mixing directional, point, and environment lights. Each scene was rendered 20 times with random configurations, like a virtual lighting lab. This variety helps the model generalize, just like humans recognize objects in different lights. The real magic happens in the encoder-decoder system. The encoder acts as a detective, gathering clues about the object's shape, while the decoder uses those clues to reconstruct the 3D surface. The key is feature consistency: how well the encoder separates lighting effects from surface details. If the encoder gets confused, the 3D model becomes messy. To solve this, the researchers introduced light register tokens, specialized attention spots, focusing on areas where lighting has the most impact, like highlights or shadows. By training the model to zero in on these regions, they improved the accuracy of surface normal maps, essentially, the direction each point on the object is facing. But here's where things get really interesting. They compared LINO-UniPS to other methods like CyclesPS-Train, PS-Wild, and UniMS-PS. And guess what? PS-verse outperformed them all. Why? Because their encoder was better at disentangling lighting from geometry, and their decoder focused on critical details without getting bogged down by noise. So what's the takeaway? This research isn't just about better 3D models, it's about teaching computers to see the world more like we do. By combining smart algorithms, creative dataset design, and a focus on high-frequency details, they're paving the way for more realistic virtual environments, better augmented reality, and even advancements in robotics and autonomous systems. Next time you see a 3D model that looks stunningly lifelike, remember, it might just be the work of LINO-UniPS. Thanks for watching, stay curious, and keep exploring the future of AI.